Cape Kennedy, Part 2. The exciting adventure into space continues from Spaceport, USA.
As each launch from the Cape brought us new knowledge, the space age moved into its 5th year. By 1964, the United States, under the direction of the National Aeronautics and Space Administration, had made remarkable progress in the space race by putting up over 50 unmanned satellites and the 6 manned Mercury satellites.
The now completed and successful Mercury program totaled 53 hours, 56 minutes, and 8 seconds for U.S. astronauts in space. But if we were to vault to the moon, it was estimated that some 2,000 hours of experience, all in Earth orbit, would be necessary, plus the mastery of joining together 2 vehicles in space. And so our next program in space became known as Project Gemini, named after the constellation which features twin stars, for the Gemini spacecraft would carry 2 astronauts seated side by side.
No longer Cape Canaveral, a new sign quickly appeared at the Cape to announce its new name. And on arrival, visitors could quickly sense the new zest and excitement as the Gemini program began its months of testing and pre-flight checkouts.
Even under the artificial lighting of night, crews could be seen working, trying to close the gap in the space race. There was no doubt that in manned satellites, the United States was behind. And while a few scientific and unmanned satellites would be launched from other NASA centers, all manned flights would continue to be launched from Cape Kennedy. And so it was here at Cape Kennedy that gains in the space race would have to be initiated. The first Gemini spacecraft, which was soon unveiled at the Cape, follows the Mercury's basic capsule design to save time and engineering effort. But since its mission requires a 2-man crew, this capsule has 50% more cabin space. This extra room also allows for the equipment which permits the astronauts to change orbit and maneuver in space, a very significant addition since the Mercury capsule was equipped only to change altitude. The capsule's pressure vessel or interior wall is fabricated from heat-resistant titanium, and its oxygen system will support the 2-man crew for as long as 2 weeks.
2 men very interested in checking out the Gemini spacecraft on its arrival at Cape Kennedy were Gus Grissom and John W. Young. For these 2 astronauts were to be its first passengers. Before human passengers can climb aboard any spacecraft, however, many tests with dummy cargoes are required. NASA's standards are high. In undertaking any mission, there must be a 90% chance of mission success and a 99.9% probability for safety of the astronauts. Like the Atlas, which launched the Mercury capsules, the Titan II has been modified slightly for increased astronaut safety. By April 1964 at Cape Kennedy, the first Gemini capsule was mated with its launch vehicle, the Titan II. This intercontinental missile of the Air Force was picked by NASA in 1961, at the time the Gemini program was planned to be the launch vehicle for this 2-man spacecraft. So on April 8, 1964, at Pad 19, Cape Kennedy, the first unmanned Gemini was launched, and the second space program of the United States had actively begun. It was an almost perfect liftoff, and the clear flame of the Titan exhaust marked the advancement being made in launch vehicles.
Since land is scarce on Cape Kennedy, the Air Force has erected a series of man-made islands in the Banana River, which flows between the Cape and NASA's Merritt Island. On one of these islands, the Titans will be assembled, which in turn will launch the Gemini spacecraft. In the Mercury and now the Gemini program, NASA has depended upon boosters built by the Air Force. Without these rockets, as well as Air Force contractors and personnel, many of the space agency's achievements would have been impossible.
As the Gemini program was getting underway, the director of NASA's launch operations at Cape Kennedy, Dr. Kurt H. Debus, pointed out the Air Force's contribution.
the majority of the rocket systems developed for military use have completed their research and development phase and are ready for their deployment and intended use. Some of these systems have been used by the NASA for the scientific exploration of space. Actually, the space program of the United States had its beginnings with some of the military boosters.
But NASA's future programs, particularly the Apollo Moon program, would demand boosters with a thrust beyond Air Force needs. So a super rocket would have to be developed. This family of launch vehicles was to be named Saturn. Soon the impact of the Saturn's development was also felt at Cape Kennedy while the Gemini program continued full speed. And for the astronauts, this construction and testing period meant continuous training to reach peak mental and physical efficiency for Gemini flights. To prepare for space missions, spacemen simulate flights in trainer devices like these. In addition to the simulator installation at Cape Kennedy, Gemini flight trainers are located at NASA's new Manned Spacecraft Center near Houston, Texas, and at Langley Research Center in Hampton, Virginia. With facilities like these, astronauts simulate as closely as possible the objectives of the Gemini program. These objectives: to gauge man's performance during flights of as long as 2 weeks in the weightlessness of space, to conduct scientific experiments in space in which man will participate, and to master the techniques of rendezvous and docking with another vehicle while out in space. In a huge hangar, pilots practice joining with another vehicle. Advanced electronic equipment enable a full-sized replica of the Gemini spacecraft to behave as if it were in space.
On the fourth manned Gemini flight, an actual rendezvous and docking maneuver will be attempted with an orbiting Agena rocket. Joining these two vehicles together while traveling 17,500 miles an hour seems difficult, but only relative speed must be considered. The Agena will be launched by Atlas missile 24 hours before the Gemini capsule. The Agena has the power to push Gemini to an altitude 2,000 miles from the Earth, far above any manned flight to date.
As yet, though, no definite date has been set for rendezvous in space. So the astronauts continue to maintain a rigorous schedule of training designed to bring out the best performance in space that is possible for Earthmen to attain.
But a training program for future astronauts and lunar nauts may take them far away from the sandy flatlands of Cape Kennedy, to places like barren desert areas, for example. In the land of the rattlesnake and the scorpion and 120-degree temperatures, spacemen train for a possible re-entry landing in the desert. Like the Mercury astronauts, the first Gemini teams are scheduled to touch down in the ocean. But just in case something should go wrong, the astronauts practice survival techniques for possible unscheduled landings.
"28 astronauts are currently undergoing extensive training such as this in preparation for Gemini and Apollo flights. In addition, NASA and the National Academy of Sciences are screening applicants for a new class of astronaut candidates to be known as scientist astronauts. These astronauts will be chosen for their science background rather than their aeronautical ability, and thus be better qualified to interpret the many aspects of space as well as findings on other planets. It is expected that a number of these scientist astronauts will soon be participating in training procedures such as this. All All this rugged training pays off, though, when liftoff time comes. This astronauts Grissom and Young know well as they entered space aboard the first manned Gemini capsule. And during this flight, Grissom became the first pilot to fly in space in the true sense. That is, actually to maneuver the ship. Yet, in fact, the Gemini program as it progresses does not directly affect our getting to the moon. It is, of course, for training our astronauts and for our understanding of space conditions. But what really counts in the exploration of the moon is the size of the boosting rocket. And it is believed that Russia's rocket goals will have only 1/5 the thrust of NASA's mighty Saturn V, now under construction for the Apollo program. NASA has established a comprehensive test program for the Saturn family of rockets, beginning with the first of this family of 3, the Saturn I, a 2-stage launch vehicle. This is number 6 of the Saturn I's as it goes through its firing tests. Each firing has a definite goal. For example, the 8th, 9th, and 10th firing of the Saturn I will carry meteoroid detecting satellites to give more information on the danger of meteoroid forces out in space. But starting in late 1965, NASA will replace this Saturn I on the launching pads with the Saturn 1B. It will also be a 2-stage vehicle, but its first stage will be more powerful, and its second stage not only more powerful, but larger as well. A series of 4 manned flights in the Apollo spacecraft is planned for the Saturn 1B. The Apollo 3-man capsule will be twice the size of the 2-man Gemini capsule. Then the mightiest of the Saturns will command full attention at Cape Kennedy, the Saturn V. After a series of unmanned flights, it is hoped that the 3-stage Saturn V, with its 7.5 million pounds of thrust and power, will boost the first men to the moon.
The 3 stages of the Saturn V moon rocket will be assembled in the world's largest building. It stands 52 stories tall, covers 8 acres on NASA's Merritt Island, and encloses 125 million cubic feet. It can house 4 erect Saturn V's. Inside, the air must be kept in constant motion to keep clouds from forming and rain from falling. Engineers will do all of the assembly work on the Saturn on large launcher umbilical towers, which can be moved from place to place. Now, this new technique does not tie up launch pads for long periods of time. A crawler transporter will pick up the 444-foot towers, complete with Saturn V rockets, a total load of 12 million pounds, and move them to the launching pads. By comparison, earlier vehicles were assembled on the pad where they were to be launched, and since that process takes months, no other vehicle could use the stand during that time. There are 3 new enormous launching pads for the moon project on Merritt Island. These pads are placed 8,700 feet apart down the beach from the old Mercury pads. The last in line is about 15 miles from the tip of Cape Kennedy.
But Cape Kennedy is only the final assembly point for what is considered the greatest single undertaking this country has attempted. For example, the journey for the Saturn to Cape Kennedy comes by way of such places as Huntsville, Alabama. By barge encased in metal, a Saturn I booster makes the trip to Spaceport, USA, along the Tennessee and Mississippi rivers, the Gulf of Mexico, and up Florida's sun-bronzed intercoastal waterway. Tugs bob before and aft as the barge, the Promise, moves closer and closer to docking facilities. The capsules, modules, and boosters which are assembled at Cape Kennedy, like this Saturn booster, come from somewhere else. More than 5,000 of the nation's industrial firms are directly involved in the construction and planning efforts to place men on the moon. The National Aeronautics and Space Administration estimates that 20,000 companies and 300,000 people will eventually participate. In addition, all of NASA's 10 major centers contribute to this effort, which, like the Saturn booster, is directed toward a launching performance at Cape Kennedy. From the West Coast, the world's largest airplane flies in the smaller upper stages of the Saturn to Cape Kennedy. This arrival is always a welcome sight, and a waiting crew quickly guides this remodeled and enlarged clipper to a safe landing. She is appropriately called the Pregnant Guppy. As the plane is opened, the smaller upper stages of the Saturn are revealed. Thus, the science of aeronautics, which took flight with the achievement of the Wright brothers at Kitty Hawk, North Carolina, comes full circle as it now serves the needs of its offshoot, the space age. And these needs are just beginning. It is predicted that within the next 20 years, the space industry will employ more U.S. workers and demand the specialized services of more firms than any other industry. As President Johnson has said,
America's commitment to the exploration of space for peaceful purposes and for the good of all mankind is a firm commitment. Our space technology and research have moved forward rapidly and dramatically since the early days of the age of space. But our achievement and our accomplishments in this field remain in their infancy.
And looking ahead in the space age, which is not yet 1 decade old, we can not only speculate about what the far future will bring, but also reflect on our present space technology. Now, all of this goes back to Sir Isaac Newton's third law of motion, which says that for every force acting on a body, there is always an equal reaction in the opposite direction. And so the thrust of a rocket is the reaction to the pressure of the exhaust gases streaming from the rocket's engines. Consequently, for energy, every rocket in use today uses a chemical fuel, either liquid or solid.
But the space industry is working toward more powerful engines. Electric engines, such as the ion engine, are being tested. It has already been verified that this ion engine, which runs longer on less fuel, can efficiently produce thrust in space. And while the thrust of an electrical engine is not very great, it can run continuously for days at a time, and in this way provide the acceleration needed for a satellite to reach such faraway places in our solar system as Jupiter and Saturn. Recent experiments with nuclear engines have been hailed as the greatest advance in rocket propulsion since Dr. Robert Goddard experimented with rockets in the 1920s and 30s. And beyond this mighty nuclear energy, scientists are now seeking ways to collect and transform into propulsive thrust the enormous quantities of free energy distributed by the sun. For if we are ever to move outside our solar system to the nearest stars, new sources of energy must be developed for the rockets of the future.
But the pending journey of the Lunarnauts by 1970 will not require such advanced technology as nuclear engines or solar power. So we return from such speculations to launch site Cape Kennedy and trace next the exciting journey of the Apollo on its path to the moon.
From Spaceport, USA, Cape Kennedy, the mighty Saturn V launch vehicle will lift off, hopefully before 1970. The thunderous roar may well be heard as far as 50 miles away. At first, it will seem to hover over its launch pad. Then, with a tremendous surge, the 7.5 million pounds of thrust of the first stage engine will push the Apollo spacecraft with its 3-man crew upward. At an altitude of about 200,000 feet, the first stage abruptly shuts down, and the second stage ignites to push the spacecraft at even faster speed. At more than 80 miles altitude, the second stage shuts down, is cast off, and the third stage ignites and burns just long enough to put it and the spacecraft in a temporary Earth orbit. Then this third stage shuts down, but remains attached to the Apollo spacecraft. Computers on Earth determine the correct time for the third stage to fire again and shove Apollo out of Earth orbit and on a course toward where the moon will be 70 hours later. Now a most intricate maneuver takes place. With the skill of long practice, the astronauts detached the command and service modules of the Apollo from the third stage of the Saturn and linked them with the lunar excursion module. Only then is the now useless third stage left behind. During the 3-day flight to the moon, the astronauts will work on overlapping shifts. Shortly after the third day, the Apollo will be caught by the moon's gravitational field and thus begin to speed toward its surface. 2 of the astronauts pass from the command module into the lunar landing vehicle without going out into space. Preparing for landing, the astronauts separate the lunar module from the Apollo mothership. By firing the descent engine, the lunar module is thrust down toward the moon. While the craft hovers, the 2 men stare out from their viewing ports, scanning the surface. They know their fuel supply permits only 2 minutes to decide on a landing or a return to the mothership. But the terrain looks safe, and in a torrent of flame and dust, they land on the moon. The commander, burdened with cameras, scientific equipment, and a life support backpack, treads the lunar dust and stands in awed immobility. An eerie twilight bathes the ancient rocks and craters of the barren lunar landscape. When the time comes to leave the moon, anywhere from 4 hours to 1 day after landing, the men climb back into the lunar module and go about rejoining their third traveling companion. The 70-hour journey home proceeds on course toward a corridor in the Earth's atmosphere, 300 miles wide and 40 miles deep. Then the service module is jettisoned. Small jets around the conical afterbody of the command module give the commander the ability to fly the spacecraft during descent. When down to 100,000 feet, a cluster of 3 large parachutes billow out from the top of the module, and the Apollo gently floats down to the ocean waves. But months and months of building, assembling, and planning at Cape Kennedy and across the United States will be necessary to make this moon trip possible by 1970. At times, the whole idea seems almost beyond comprehension, and Cape Kennedy seems to become a hazy architectural fantasy land of gantries and towers and launching pads. Yet, paradoxically, most of us have assumed sort of a sophistication toward the space age, as if we're no longer cognizant that this is the most ambitious scientific undertaking that has ever been attempted. Just how far the space age has come in so short a time is perhaps best comprehended by looking back at Cape Kennedy as it was in the early 1950s, back when Dr. Kurt H. Debus was supervising the first missile launches from the Cape. Today, Dr. Debus is still supervising our space launches at Cape Kennedy, but it has now become Spaceport, USA. And the lighthouse that once was the focal point at Cape Kennedy has been overshadowed by a light that will guide man through the universe and the heavens beyond.
In the exciting space race, we have embarked on a long road from which there can be no turning back. As the stars beckon, we try to evaluate how the space adventures of today will affect our way of life tomorrow. Now, no one can answer this question for us. The greatest venture that man has ever made into the unknown is still a tantalizing mystery. Perhaps this is the appeal, the wonder, and the fascination that draws us ever closer to Cape Kennedy.